Hi everyone, hope all of you are doing great today. Thanks for the commit to give me the opportunity to present our work on immunomodulation with fast presenting biomaterial achieves pancreatic islet graft tolerance in a non-human primate model. As we know, pancreatic islet transplantation can restore the beta cell mass in type 1 diabetes with potential for prevention and reversal of diabetic complications. However, there are many challenging issues such as inadequate islet supply, need multiple donors per transplant, the innate and adoptive immune responses. Also, especially the current immunosuppression agents are not only toxic to the patient, but this medication are especially toxic to the beta cells, and they may even induce peripheral insulin resistance. Because of these risks, islet transplantation has been limited to patients with severe disease of hypoglycemic awareness because we have to balance the benefit versus the risk. The full potential of islet transplantation will not be actualized until islets survival can be secured without chronic immunosuppression. This presentation will be primarily focused on localized immunomodulation of innate and adoptive immune responses for sustained survival of allogenic islets without chronic immunosuppression. Our collaborator Dr. Garcia and Georgia Tech, Dr. Havo and Yunchai and the University of Mizzou previously reported a biomaterial called PEG-SA FasL can promote long-term islet acceptance in mural without chronic immunosuppression. So in this study, our objective is to investigate whether this strategy can be translational in a relevant preclinical NHP model. Just wanted to point out that the core function material here is FasL. The PEG and SA are used as the vehicle of FasL. Before I dive into the non-human primate study, I here review a little bit of background information first. We know activation-induced cell death is an important pathway for immunohemostasis. When T cells are activated, FAS will be expressed on the surface and then become sensitive to apoptosis induced by the FAS-FasL interaction. FAS-FasL interaction has been long studied in the area of the immunoprivilege and tolerance to the self-antigen. Actually, there is no compensatory mechanism because for subject has FAS-FasL deficiency will suffer lymphoproliferation and autoimmune disease. As a type 2 member protein, FasL can have two opposite roles. For membrane-bounded, it can function as an immunomodulatory to physically eliminate T effectors. However, its soluble form can be anti-apoptotic and chemotatic. All these characters have led to intense study with FAS-mediated apoptosis as a means of treat graft rejection and autoimmunity. When come to use FasL to induce apoptosis to block T effector cell killing to prevent organ or tissue rejection, people have tried to use gene therapy strategy to overexpress FAS in cell or tissue, but this is technically difficult to do itself, also difficult to get regulatory approval for clinical application because it is uncontrolled continuous expression of FasL, which possesses pleiotropic function, depends on its form as membrane or soluble. And years ago, our collaborator Dr. Havo and Dr. Yunche applied a strategy to apply FAS locally by conjugating FAS on the surface of islets to block FAS-positive T effectors from killing islet graft, which showed long-term graft survival in combination with a short course of rapamycin. The graft survival is also associated with expansion of T-reg cells locally. Recently, our same collaborator, Dr. Garcia, Havo, and Yunche applied a different strategy for the local delivery of FAS. Instead of modifying islets with FAS ligand, they used an advanced synthetic material, a PEG microgel, to deliver FAS within the graft microenvironment on a controlled and sustained fashion, which achieved long-term graft survival when combined with a short course of the rapamycin. So, in brief, there are three strategies to deliver FAS ligand, especially when it comes to protect islets. We can just modify the islets, but have the potential to affect its viability if it's not done properly, or encapsulate the islets with FAS ligand microgel, which might impact the nutrients diffusion. Or the last strategy, just use a microgel carrier FAS ligand to co-transplant with its islets. Obverse, the last strategy is most translational. In our NHP study, we adopted the strategy for co-transplant of FAS ligand presenting PEG microgel with unmodified islets as we did in the mirror model. Graph A is a scheme drawing to show how islets and microgel will transplant. The synthetic biotin PEG microgel generated by microfluid polymerization capture and present SA FAS ligand, and then SA FAS ligand presenting microgel is co-transplanted with islets mobilized on the surface of omentum of NHP with autologous plasma and thrombin, where they form a microenvironment to induce immunoacceptance. Specially point out is that we put islets onto omentum shown as graph C, not as the conventional transplant in the clinic, which islets goes to the liver. Doing so for the reason of the safety to avoid not only the potential complication the microgel might cause, also avoid harms the liver usually does to islets when they are lodged in the liver. The treatment protocol is shown as graph B is SA FAS present microgel with transient rapamycin monotherapy. Control group just received empty microgel, no FAS, with the transient rapamycin therapy post-transplant as well. I would like to point out, after transplant, animal only on rapamycin monotherapy for first 3 months post-transplant. After that, there is no any immunosuppression for the experiment group, not like the conventional clinical practice with 2 or 3 immunosuppression drugs to protect graft from rejection. Here it shows the graph D, or the control animals reject the graft around 1 month, but about half years later, the FAS microgel animals still have great graft function. But due to the logistic constraint caused by the COVID-19, we had to terminate our study animal prematurely while grafts were functioning for the experimental group. This slide summarizes the graft metabolic performance of both experimental and control group animals. Graph A shows the mean graft survival times. The FAS ligand microgel group greater than 180 days. The microgel control group just 27 days. Graph B shows non-fasting blood glucose level and the daily external insulin requirement for FasL microgel animals. Animals exhibited high blood glucose level and high external insulin requirement after the STZ induction before transplant. After transplant, animals rapidly become normal glycemic and had a significantly reduced external insulin requirement. Animal reverted to the hyperglycemic state after graft removal. The graph C shows blood glucose dynamics for these animals on IV infusion of glucose test and different time points during the study. Here we can see, and before transplant, glucose doesn't come down during the 90 minutes test time, and 3 to 6 months post-transplant, the glucose disposed are as potent as when animal was naive, then returned to uncontrollable status when grafts were removed. The graph D shows insulin and C-peptide in the serum for the fast microgel animals under fasting and the post-stimulation at different time points during the study. We can see here, after STZ induction, there is no insulin and C-peptide secretion, but it recovered after transplant, then become undetectable again after removal of graft and the end of the study. All this metabolic data shows grafts were still functioning around 180 days post-transplant for the fast receiving animal before study ended. The graph E shows non-fasting daily blood glucose level and insulin usage for the control group animal who just received the microgel. After restore the normal glycemia following the transplantation, animal become hyperglycemic and require high external insulin around 1 month post-transplant. The graph E shows animal lost blood glucose control during the IVGCT test and 1 month. The graph G shows no insulin and C-peptide level and 1 month either. So what this data indicate, the graft were rejected around 1 month for the control animal. This slide shows data for individual NHPs received fast microgel. The graph A to D shows the non-fasting blood glucose level and the daily insulin requirement for each animal. We can say after transplantation, all animals rapidly become normal glycemic and only need 10 to 20% of the pre-transplant external insulin level. Each animal reverts to the hypoglycemic status again after graft removal. Graph D for the animal 9118 achieved almost full insulin independence with time passed by. Graph E to H shows the stable body weight during the study. The graph I to J shows the serum level of the SA fast ligand in all subjects, which reached to the background level between 7 to 14 days post-transplant. And the graph M shows well-controlled HbA1c during the study course. This slide shows data for individual NHP received the control microgel, which means no fast. Graph A to C shows after transplant, animal restored normal glycemia, but become hypoglycemia and require high dose of the external insulin again around 1 month post-transplant. The graph D to F shows the body weight downwards first 30 days post-transplant. This slide is the histological analysis of graft. The graph A shows well-preserved islets structure in the experiment group and with minimum cell infiltration. However, the control animal showed ruptured islets graft with heavy cell infiltration. The graph B shows the FOXP3 staining, should increase the FOXP cells and the graft site of the experiment animals. The graph C and D is a quantification of the FasP3 cells, shows they have higher frequency in the experiment group. We found the local delivery of SA FasL does not alter the peripheral blood lymphocyte population. The experiment group is in blue line and the control group is in the red line. The number of circulated CD3, CD20, and CD4, CD8, as well as the naive T cells, the effector memory, and the central memory, or no significant changes. Here shows the fast Microgel animal displayed no significant changes in the pre to post-transplant anti-donor MHC antibody, CD4, CD8, mixed lymphocyte reaction, and interferon gamma secreting cells, no change either. However, shows graph B, the control animal generated antibody against the donor MHC class 2. This animal also even not exhibited response against donor was 30 part in the antigen in the CD4 cell compartment, but the CD8 cell response were elevated against both the donor and the third part stimulator. We monitored both cytokines and chemokines in serum for both group animals. No significant difference to pre-transplantation concentration were detected. Graph A to D, it's each individual animal shows positive SA FasL antibody. The graph E shows the IgG is mostly from the SA component of the whole SA FasL molecule. Histology and graph A shows normal morphology of various organs, no toxicity of FasL administration. The graph B shows negative insulin staining in the pancreas and necropsy and 6 months post-transplantation, which means no endogenous islets to provide the insulin during the study. Here, the graph A to C shows stable blood BUN creatinine and ALT level in these two groups of animals, which indicate no detected toxicity of FasL to both liver and kidney. The graph D and E shows comparable RAPA level in these two groups of animals. In conclusion, we sought to use the immunomodulatory material of SA FasL present Microgel as a means to promote tolerance in a relevant preclinical transplantation model. This study succeeded with unmodified islets, does not require long-term continuous of the systemic immunosuppression for graft survival. The SA FasL present Microgel are safe and also easily be prepared as an off-the-shelf product, making it reliable and distributable. These are the critical considerations in the translation of this strategy to the successful and broad clinical application of islet transplantation for the treatment of the type 1 diabetes. Many people have contributed to this project. From Dr. James Markman's group and MGH, Helen Zhihong greatly contributed to the daily NHP study. Tim and Dr. Garcia's lab from Georgia Tech made the Microgel. Tim from Dr. Xiaowang and Yongqia's lab from University of Missouri made the FasL. Also, thanks to our major funding agency, JDRF. Lastly, special thanks to my chief and mentor, Dr. James Markman, for all the guidance to make this project successful. Thank you everybody for your attention.